Good morning, all of you on the West Coast. Good afternoon to everyone else. So let me go ahead and share my slides. Okay, again, thank you everybody for joining us today. My name is Bob Sinkovitz. I'm here at the San Diego Supercomputer Center, and we're going to be presenting a new topic, something we haven't presented before, called using regular expressions with Linux tools. And as Cindy mentioned, she provided links to the slides and to the GitHub repo in the chat. So just a little bit about Complex. This is an NSF-funded program. We've been active for about close to a year and a half now. The idea was that we are providing training in non-programming skills that we feel are needed to effectively use supercomputers. So topics like parallel computing concepts, Linux tools, bash scripting, security, batch computing, how to get help, data management, and interactive computing. All right, so a little bit of introduction. Regular expressions, also known as regexes, provide a way to identify strings that match a specified pattern in a body of text. And they have their foundation in formal languages and theoretical computer science. So although the regex formalism may seem daunting, these regexes, they have a lot of practical applications for computational and data scientists. So in practice, the implementation of regular expressions in computer languages, text editors, and Linux utilities goes well beyond the original definition to allow for more complex patterns, back references. So while the syntax and the feature set for regular expressions can vary across languages, the basic concepts that we're going to be covering are universal. But in this tutorial, we're going to focus specifically on their implementation and Linux utilities such as awk, set, and grep. So why do we need to understand regular expressions? So you can get by without regular expressions, but knowing how to use them can make your life much easier, especially when you combine them with really powerful tools like awk, set, and grep. So if you're a data scientist, you probably spend much of your time performing the mundane tasks to filter your data, get into a usable form. It's often referred to as ETL, extract, transform, and load. So regexes, they'll allow you to create more compact and robust scripts. Now, if you're a computational scientist, regexes will be helpful when extracting important information from the results of your simulations or when preparing input files for high throughput computing workloads. And I'm sure that your use case is much better than I do. And hopefully by the end of this talk, based on what you learn, you might come up with new ideas of how you could use regular expressions in your own work. So I'm going to say this is going to be a gentle introduction to regexes. So entire books have been written on regular expressions, and you can spend days, weeks, even months going really, really, really deep. About 2 decades ago, I had read the O'Reilly book, Master in Regular Expressions. It's about 400 pages long, very, very dense. I did it sort of as a hobby project. I don't necessarily recommend that you spend that much time on regular expressions. I had a little bit of free time on my hand. We're not going to do that. You're computational and data scientists. You have other priorities. I know that many of you are graduate students and you want to finish your thesis work. You're working on NSF or NIH projects. You just want to get your work done. So we're going to focus, I think, what are the basics and which will satisfy most of what you need to do with regular expressions. But again, if you ever do decide that you want to go really, really deep, well beyond what we're covering today, I suggest that you take a look at Master in Regular Expressions, this book, or other resources that you could find online. So prerequisites. We really feel that you're going to get more out of this session if you're already familiar with tools that use pattern matching, such as grep, sed, and awk. If you're here already and you don't have that background, we'd recommend, maybe go back, attend the complex webinars on Linux tools for text processing, or work through the materials that are posted online. You could watch previous videos, and then maybe go back and review this material. Okay, so we're going to start with the regular expression formalism. Now, I was looking at the list of registrants, and we had more computer scientists than usual. So for the computer scientists, this might already look familiar. So a regular expression, a regular language is a formal language that can be defined by a regular expression and has the following definition over an alphabet sigma. And when you see examples of regular expressions that start with this formalism, they're usually very, very abstract. What they mean by regular expression or a regular language is a collection of strings formed, say, from A's and B's that meet certain requirements. So we say that the empty language is a regular language. For each element of sigma, so basically A but belongs to sigma, the singleton language consisting of that single character is a regular language. If A is a regular language, A star, where the star is actually the Kleene star, is a regular language. So due to this, the empty string language is also regular. If A and B are regular languages, then the union and the concatenation are also regular languages, and no other languages over sigma are regular. So that's very, very abstract, but it does provide the foundation for what we're going to be covering today. So regular expressions, though, in real life, unless you do theoretical computer science or linguistics, you probably won't start with the regex formalism. Instead, you will work with regular expression engines that provide an augmented syntax for constructing patterns. So if we go back here, it doesn't have it in the definition, but when we're constructing regular languages, in addition to the alphabet, the only two operators that we have are the Kleene star and the vertical bar, which means alternation. But when we work with regexes in real life, we're often gonna augment that original formalism, and we're gonna have a much richer syntax for constructing patterns. So today we're gonna cover everything that we see here in the table. We're gonna look at quantifiers, the asterisk or Kleene star, question mark, plus, and in curly braces, and we'll explain this a little bit later, where we can specify exactly n repetitions. We can specify ranges, and these can be open-ended, from nmin to nmax, nmin or larger, or up to nmax. We're going to have a period, which represents a wildcard. We're going to see anchors, the caret and the dollar. We're going to see ways to specify multiple characters and negation of a set of characters. We're going to look at character classes, grouping, and then finally alternation. But strictly speaking, it's just that asterisk or Kleene star and the vertical bar for alternation that are part of the original regular expression formalism. So a few words about grep before we dive in. So we're going to start with grep, which is the simplest Linux utility that does pattern matching. Now, most of what we cover in grep is also going to apply to more complex tools like awk and sed. So if you're not familiar with grep, it's a tool that returns all lines from a file that match a given pattern. For the purpose of this webinar, it can be more instructive, though, to see what portion of the line resulted in the match. So to do this, we're going to configure grep to colorize the output. And if you are, if you're working on Expanse, I believe that that we already have the environment set up so that grep points to grep -- color equals auto. So what that means is that the matching portion is going to be displayed in red on the terminal. Now I know that not everybody sees the same set of colors, so if you prefer, you can even set the color to something other than red. You could do export grep colors equals mt equals 1 comma xx, where xx is set to 32 for green, 33 for yellow, 34 for blue, 35 for magenta, and 36 for cyan. So throughout this presentation, the grep matches will also be underlined to emphasize the white space captured by the match, and also to highlight the results for folks who don't see red as well as others. But I should mention, this underlining is not a feature of grep. It's just something that I did in this presentation to make the results easier to visualize. Okay, so if you've ever used grep, awk, or sed in any form, you've already used the very simplest regular expressions. So the simplest regex is just a literal string. Note that by default, grep matches are case sensitive. So in the Linux world, everything is case sensitive. So, and these examples are all in the GitHub repo that Cindy posted a link to in the chat. So if you go to the into the repo, you're going to see a file, fruit.txt. They do a lot of fruit examples. And in that file, you're going to see a number of lines listing 3 fruits. So apple, banana, pear, cherry, banana, peach, orange, lemon, lime, and so on. Notice though that we have banana both starting with lowercase b and an uppercase b. So if we do grep on the right side of the screen now, grep banana, all lowercase fruit.txt, we're going to see 2 matches. So it matches banana with a lowercase b, but not banana with an uppercase b. And then the next example, we explicitly search for banana with an uppercase b. So this is going to match banana with the uppercase b, but not lowercase banana. And just a reminder that the grep matches, they're underlined and they are shown in red. We do this both for visibility and also for some later examples to emphasize white space or punctuation that may have been captured by the match. So the first thing that we're going to do in really exploring regular expressions is we're going to look at matching choice of multiple characters. So grep has an option, -i, to make the matches case insensitive. Now sometimes this is what you want, but there might be unintended consequences. So the regex way of doing this is to provide the upper and lowercase options in square brackets, which gives a finer degree of control. So again, on the left, we show the contents of the fruit.txt file. And on the right, we show first that they're doing a search with the -i option. So this is going to match banana starting with a lowercase b, banana starting with an uppercase b. But if this file also contained other mixed cases, say banana in all uppercase, or the first 3 letters uppercase, or BA, capital N, A, capital N, A, and so on, all of those matches are going to be captured. Now, by using a regular expression, though, we have finer grain control. So if I wanted to find just what we consider the standard spellings of banana, all lowercase with the first letter either lower or uppercase, I could take those 2 options, lowercase b, uppercase b, and close those within square brackets followed by AN, ANA. So we can generalize this. In that first example, we just use the square brackets to define a set containing 2 characters. But we can specify an arbitrary set of characters that satisfy a match. If we proceed with a caret, that's going to exclude the character set. Now, this is one thing about the regular expression syntax that's just a little confusing. The caret is used in 2 different contexts. Here we're using it to exclude a character set, but we're also going to see how it can be used as an anchor. So let's take a look at another file. I called it ash.txt. The naming because the file contains a list of words that all end with ASH, but begin with different characters, B, C, D, G, H, L, M, R, W, and finally a dash. So if I do grep and then in my square brackets, BDRW ash, and operating on the file ash.txt, we're going to see that we're going to find all the matches of B, D, R, or W followed by ash. Now, if I use the caret within those square brackets, that's going to exclude the character set. So now we're going to match any character except B, D, R, or W followed by ash. And notice that in this case that we also picked up hyphen ASH. Now we can also specify ranges of characters using the syntax, again in square brackets, x-y. And like the previous example, the caret indicates negation. And if we want to match a dash or a hyphen, we make it the first or the last character. Otherwise, it would be interpreted as, in the context of specifying a range of characters. So going back to our file, ash.txt, containing ash preceded by various letters and a dash. We're going to start off grep, and again in our square brackets, D-H ash.txt. So now we're going to get matches of letters D through H followed by ash. And these character ranges operate exactly as you would expect. Letters follow alphabetical order, digits follow numerical order. Now, if we wanted to match any character except C through R followed by ash, we could use the caret and inside the square brackets. So in this case, grep in the square brackets, caret C-R, and now we see bash, wash, and hyphen ASH. And then finally, if we wanted to include matches that include the dash, notice that here I included the dash as the first character within those square brackets, again, so that it's not interpreted in the context of specifying a range. Then I have G-L to round out the character set. So now we're going to get matches of G through L and the dash followed by ASH. So let me just pause here and see if there are any questions.
No questions at this time, Bob.
Okay, great. Thank you, Cindy. All right, so we're going to continue on this theme, the matching choice of multiple characters. So regular expressions recognize the standard POSIX character classes, but sometimes you may find it just easier to use in square brackets A through Z, capital A through Z. You can see in the next example here, lowercase a hyphen lowercase z, uppercase a hyphen uppercase z. So when we define these character classes, we could actually specify multiple ranges within those square brackets. 0 through 9, and then finally in the last example, we look at all of the alphanumeric characters, lowercase letters, uppercase letters, and digits 0 through 9. So now we're going to look at another file, oot.txt. And again, all of these are contained in the GitHub repo that we shared earlier. So you'll see that we have this string OOT preceded by a few lowercase letters, B and C, a couple of uppercase letters, F and H, a couple of numbers, and a couple of punctuations. So instead of using A-Z or capital A through capital Z, we could use these POSIX character classes. So in the first example, we have grep, double square brackets, colon, lower colon, oot.txt. In the next example, we use colon, upper colon, and then finally in the last example, we use colon, alpha, colon. So these are lowercase letters, uppercase letters, and all letters, lower or uppercase. Now, one stumbling block with the syntax is you'll notice that we have that we use pairs of square brackets rather than a single set of square brackets. The reason is when we take square bracket colon lower colon square bracket, that's going to be expanded into the list of letters A through Z. Now, since that is a set of characters, we actually need to enclose that within the square brackets so that grep will work as expected. Now, in the last column of examples, we see an example you identifying digits. So again, pair of square brackets, colon, digit, colon. Again, I find it easier to just remember 0 through 9 or A through Z, but if you prefer, you do have this option. And then next we have alnum, which picks up the letters and numbers. Now the last one though is particularly useful. So we have a POSIX character class called punct, P-U-N-C-T, which will match all the punctuations. This is really, really handy because otherwise you would need to, if you're looking to match all of the possible punctuations, you would have to go through your keyboard and manually type all of those in. The period, colon, semicolon, comma, question mark, exclamation point, percent, pound sign, and it would be very, very easy to miss some of those. And we're going to see an example a little bit later where we might want to use the punct character class. So have a listing of what I consider the important character classes here. So we've seen a few of these: upper, lower, alpha, digits, alnum, punct, blank, which is spaces and tabs, and space, which is all white space characters. So I find, again, these last three here, punct, blank, and space, to be extremely, extremely useful. The difference between blank and space is that blank is going to be just spaces and tabs, whereas space is going to be all white space characters, which includes new lines. All right, so moving on, a single dot matches any character except a new line. So we're going to do a few more searches. We're going to go back to fruit.txt. So we're going to do B followed by 4 periods, followed by A, and that's going to pick up the two lines that contain banana, starting with the lowercase b. In the next example, we're going to start with a period, E, 2 periods, and H. So this is going to pick up all instances of the string peach. And then in the last example, we're going to do .ea dot. So this is going to find all strings of any character followed by EA followed by any character. Now notice that in this last example that we picked up pair, and then the second line we also picked up the first 4 characters of peach. So the match wasn't peach, it was just PEAC. In the second line from the bottom, notice that we actually have 2 matches. So the way grep will work is that it will identify all matches for that regular expression within a line. So this is important to keep in mind. Often, we only care that a line contains a match, but there's a really useful feature. We could use the -O option that lets us capture the actual matches so that we can then use those results for further processing. Now, quantifiers, this is, I feel, where we're really getting into the meat of regular expressions. So everything we've done up to this point involve matches of fixed length. Now, quantifiers allow variable length matches and provide a lot more flexibility. So we're going to start off with the asterisk, which is 0 or more of the preceding element. The plus, which means 1 or more. Question mark, which means 0 or 1. And then in curly braces, if we have a single integer, that means we're looking for exactly that many repetitions. If we have an integer followed by a comma within the curly braces, that means that we're looking for at least n-min matches. We could also do comma n-max, which means we're looking for at most n-max. And if we use n-min, comma n-max, that looks for matches anywhere from n-min to n-max. So we'll look at a few examples to make that a little more concrete. So in this table, I'm showing matches using these quantifiers. So in the first example, we have AB star C, which means we're looking for A followed by 0 or more B's, followed by C. Now in the next example, we're using the plus sign. So we have AB plus C. So this means that we want A followed by at least 1. So 1 or more B's followed by C. In the third line, we have AB question mark C, which means that we want A followed by 0 or 1 B followed by C. And then in the next 4 lines, we use the curly brace notation. So looking for match containing exactly 3 B's, 3 or more B's, up to 3 B's, or 3, 4, or 5 B's. So we're going to look at a few concrete examples. So if you go to the GitHub repo, you will see a file abc.txt which contains the string AC with varying numbers of B's in between. So a single B, 2 B's, 3 B's, 4 B's, and 5 B's. And all of the examples that I have here, all of the grep commands and then awk instead when we get a little bit later into the presentation, that's all contained in the repo too. So if I go through those examples from the previous slide, we see in the first one, AB star C, we pick up everything from AC to A followed by 5 B's and a C. In the next example, AB plus C, we see that we get the strings that contain at least 1 B. AB question mark C, the matches where we have 0 or 1 B's. And then in the last column, we see examples of at least 3 B's, up to 3 B's, or exactly between 3 and 5 B's. And I see there's a question in the chat. Let me go take a look. Oh, Al-Bashir, so what is the -E flag for? Great question. I'm going to be covering that in the next slide. So it's like you were reading your mind, reading my mind. So what's with the single quotes and the -E option? So I know that I threw something new at you there without explaining it right away. Here's where things get a little complicated with regular expressions. They come in multiple flavors. So we have what we call basic regular expressions, extended regular expressions, and Perl compatible regular expressions. So by default, grep uses basic regular expressions, or BREs, which require that the following characters be preceded by backslashes. And that's the parentheses, the curly braces, the plus, the question mark, and the vertical bar for alternation. So if we wanted to look at a match of A followed by anywhere from 3 to 5 B's followed by C, the way we would have had to written that was AB backslash left curly brace 3, 5 backslash right curly brace C. The E option tells grep to use extended regular expressions, which don't need the backslashes. So in this case, grep-E, and then in single quotes, AB, curly brace 3, 5, C. So the single quotes, they're going to prevent the Linux shell from interpreting the special characters, so that they're passed to grep. So if you've used grep in the past, say to do very simple searches, looking for fixed strings, you probably didn't use the -E and you probably didn't use the single quotes, but they just allow us to write much cleaner regular expressions. So does that answer the question?
Looks like you got a thumbs up.
Okay, perfect, thank you. So let me go back here. All right, so I'm going to recommend that when we start doing more complex regular expressions, use the dash capital E option and enclose your regular expression in single quotes. Oop. Okay, so if you remember in the beginning of the presentation, we talked about the regular expression formalism, and the only operators that we have are the asterisk, or the Kleene star, and the vertical bar. So you strictly don't need the plus, the question mark, and the curly brace notation. So you could theoretically do all of your regular expressions just using the asterisk and the vertical bar, but life is going to be much easier if you use the full set of available quantifiers in your regular expressions. So we're going to show a few examples here. In the first column, my original regular expression, and then in the next column, using only the asterisk quantifier and the interpretation, which you saw already. And I should have put the, I should have filled in that block in the first row. I didn't, since the original and the one using only asterisk and vertical bar were identical. So if we wanted to avoid the plus, we could have done A, B, B star C. So what this means is that we're going to have at least one B followed by 0 or more B's. If we wanted A optionally followed by a single B followed by C, we could have done AC, vertical bar, ABC, and then so on. I won't read everything out here. You could see that these regular expressions become very unwieldy if we're trying to do matches like A followed by 3 to 5 B's followed by C. And they're also a little bit harder to read. So if I look at that the third example, AB question mark C, you know, it's a little less, at least to me, a little less obvious what we're doing. And a little bit of geek trivia. I've mentioned this a few times, been calling this star the Kleene star. So the star in a regular expression is called the Kleene star, named after the American mathematician Stephen Cole Kleene. Kleene is pronounced the way I've been saying it, Kleene. I would look at this and think that it was clean. So if we have any computer scientists here, you probably heard this already. But if you're not a computer scientist, I think your comp sci friends will be impressed. But if you call it a star or an asterisk, everybody's still going to know what you're talking about. So, you know, obviously, Kleene was a very, very accomplished mathematician, you know, smart enough to get an asterisk named after him. All right, so we're going to get now into one of the subtleties of regular expressions, and that is that quantifiers are greedy. So by default, a quantifier is going to try to find the longest possible match. So in the example below, we start scanning the line from left until we find the first P, and then from the right until we find the first R. So we're going to go back, we're going to look at our file again, containing fruits. You know, each line has 3 fruits. And we're going to do a grep, P dot star R, which means P followed by 0 or more characters, any character, followed by an R. And the results might have been a little, maybe not quite what you were expecting. So you might have written this expecting that you're going to find matches for pair. But what actually happened is in those first couple of lines, we picked up the first P in apple all the way through that last R in pair. So again, these expressions, they're greedy. That asterisk is going to expand and look for the longest possible match. You know, if we look at the third line, we start with the first P in pair and extend through the R in grape. And then it's only in those last couple of lines that we got the match that we expected. Now, I have a couple of asterisks here. It's more complicated than that, and we can go down a rabbit hole of backtracking and finite state engines. But if we only have one quantifier in our regex, this is a close enough working explanation. So if you go back to that O'Reilly book that I mentioned near the beginning of the presentation, they go very, very deep into this topic of how the match is found. and matches containing multiple quantifiers, depending on how they're written, they could become very, very, very expensive to calculate. So let me go. I saw a something here in the chat. Okay, yep, just good. Glad I answered your question, Albashir. All right, so let's move on. Grouping. So in our early discussion of quantifiers, recall that they applied to the preceding element rather than a character. So regexes can group multiple characters into a single element using parentheses. So we're going to look at a file, grp.txt, and here we have 3 zeros followed by various strings, followed by 3 ones. So we have an AB, we have an A followed by XYZ, B, A followed by XYZ, XYZ, B, and so on and so on. So if we wanted to look for matches of, say, one or more of the string XYZ, it would be a little difficult to do if we couldn't do grouping. So in the first example, we do a grep-e and then single quotes A, and then in parentheses XYZ question mark B. So this means we're going to look for A followed by 0 or 1 instance of the string XYZ. And then a couple more examples where we look for exactly 2 or 3, or for 1 or more of the string XYZ. Again, you could do this without grouping, but your regular expressions are going to become very, very unwieldy. And again, notice that we're using the -e option, because otherwise we would have had to precede those curly braces and the parentheses with backslashes. Now anchors, this is something that you might have seen before if you attended the Linux tools for a text processing webinar. So without any other specifications, grep looks for a match anywhere in the line, and anchors allow us to restrict matches at the start or the end of a line. So going back to our fruit example and searching for pairs, we can see in the first match, just grep pair fruit.txt, that we get 5 matches, a couple where pair appears at the end, a couple where pair appears at the beginning, and one where pair is in the middle. Now, if we use the caret before pair, that's an anchor, and then says we're only going to look for matches at the start of the line. And if we use the $, that's going to say we're only looking for matches at the end of the line. Alternation, we actually mentioned this already, but I want to cover it explicitly here. Sometimes we want a single regex that matches 2 or more patterns, such as a string that appears at the start or the end of the line, and this can be done using alternation. So going back to the 2 examples in the previous slide, we have caret pair to look for matches at the beginning, pair $, to look for matches at the end. We could have also done caret pair and then vertical bar pair $. So now this is going to pull up it's combining 2 matches. We're looking for pair at the start, and we're looking for pair at the end. Now, word boundaries. This is one of the most challenging tasks in writing regular expressions, and that's finding matches that form whole words, where the matching substring must be at the start or the end of the line, or preceded and followed by non-word characters, something other than a letter, digit, or underscore. So in the next couple of slides, we're going to look at what seems like it should be a very simple example, and that's finding lines that contain a valid 5-digit zip code. So we're going to do this the hard way first, see the various pitfalls, and then we'll look at how we can do this a very easy way with grep. So in the repo, we have a file, zip.txt, and it contains lines with valid and invalid zip codes. And by valid zip codes, I just mean a string of 5 digits. Now, if we have extra characters or extra numbers in that zip code, we're going to say that it's invalid. So in the first few lines, we're using the zip code 12345, and it's separated by spaces or punctuations, and these are all valid. Then we have a line containing just the zip code, And then in the last 4 lines, we look at zip codes that are wrong. We have an extra digit. We have a zip code that's too short. And we have a couple of zip codes, one that's preceded by a letter, another that's followed by a letter. So if I do grep-e, and then my single quotes, 0 through 9 in square brackets, saying we're looking for digits, followed by 5 in curly braces, that means I'm looking for all strings of 5 digits. So we pick up all of the valid zip codes, but notice that we picked up 3 invalid zip codes also. 1, 2, 3, 4, 5, 6, A, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, B. So one of them was too long and the other 2 had extra characters. Notice though that the matches appear to be correct. You know, we picked up the 5 digits. So we need to be aware of word boundaries. So we want to find a regex that finds all of those zip codes without any false positives or negatives. And it's going to consist of 4 alternatives. It's easy though to make mistakes when we write these long regexes. So I don't expect everybody to follow this very, very long regex right here, but you'll see that the first part is we're using the caret to look for strings of 5 digits that appear at the start of the line, and then those digits have to be followed by either a punctuation or a space. And then we have the vertical bar at the end for alternation. Then we're looking for 5 digits that are surrounded by either white space or punctuations. Then finally, the 5 digits at the end of a line, and also lines that consist, that 4th option there, of just strings of 5 digits. So this works. That this picked up all of the valid zip codes, but notice though that we also picked up some characters that we didn't want. So let's emphasize this using the -O option, and you'll see that we picked up neighboring spaces and punctuations. So I don't know of a way around this with grep, doing the way that we did, and we would need to pipe the output into another utility for further processing. Fortunately, grep and the other Linux tools have ways for specifying word boundaries. So we can delimit the match with \less than and \greater than, or \b to denote the word boundaries, or we could use the W flag to select matches that form whole words. Now my preference is for the first option, since it's going to work with grep awk instead. The W flag is specific to grep, and \b has no special meaning in awk. So now I'm going to write a new regular expression. Here within my single quotes, I have \less than 0 through 9, and then curly braces 5, \greater than. And in this case, we picked up all of the valid zip codes without getting any false matches. And I'm showing here on the right how you could have done this with the W option. Both work, but again, I like to use the \less than, \greater, since that's going to work across all of the Linux tools that recognize regular expressions. Okay, lazy matching. We talked earlier about how regexes are greedy by default, meaning that they look for the longest possible match. Lazy matching looks for the shortest possible match, and it's implemented in grep using the lazy quantifiers. Pairs of question marks, plus question mark, asterisk question mark, and with the -P option for Perl compatible regular expressions. Now you might be wondering, why Perl compatible? Years ago, Perl was kind of the default language for doing text processing and working with regular expressions. And they had a very rich set of additional capabilities, including these lazy quantifiers. So if we look at the file lazy.txt, if I do an a.*b, I'm going to get the longest possible matches of a followed by any number of characters followed by a capital B. If I use the lazy quantifiers with the -P option, I'm just going to pick up the matches of A followed by the minimum number of characters until I find that first capital B. So this is something that you're probably not going to use very often, but it's nice to know that it's there if you ever do need it. And then finally, escaping special characters. Like just about everything else in the Linux world, special characters can be escaped with the backslash. And if you forget the backslashes, the errors can be very subtle. So we're going to look at another file here, spc.txt, and notice that we have a lot of special characters in there. We have asterisks, plus signs, we have parentheses, question marks, and curly braces. So let's say we wanted to find all of the strings that that contained an X. So we could do, and then in our parentheses, dot star X, and then dot star again in parentheses. But now if we wanted to find more complex patterns that included the curly braces or parentheses, we need to escape those with backslashes. So in that second example, we're looking for 0 or more characters enclosed by parentheses, X, and then 0 or more characters enclosed by parentheses. In the next couple of examples, you can see that things didn't, or in the first example, that didn't come out quite the way we expected. I'm still trying to figure out what exactly happened here, but I think that the first curly brace was interpreted as the start of an interval syntax, followed by 1 or more digits, then a literal close in parentheses. But the result is not what we wanted. In the final example where we use the backslashes, we're getting the match that we want. Okay, regular expressions with awk. Just about everything that you learned so far with grep is also going to apply to elk. Now, curveball here though is that the default flavor is extended regular expressions, which we enable using the -E flag with grep. And the regex is going to be delimited by slashes. So if you don't remember awk, don't worry about this too much. The general syntax of an awk command is a pattern followed by an action. So here we're looking for, on the left, we're looking for matches of strings that contain a pair at the beginning, pair at the end, and we're printing them. In the other example, we're looking for A followed by 3 or more B's followed by C. And then we didn't really get into any of the other features of awk. But again, main thing we want to point out here is that you can use regular expressions here in the pattern match, and that regex is enclosed within slashes. And we can also do regular expressions in sed. Here's where it gets a little confusing, but like grep, the default is basic regular expression instead of extended. So you can use the -E flag to get EREs so you don't have to escape special characters. So just showing an example here. So really we're not getting into awk and sed, just want to mention that you can use the regular expressions with those tools. So this is a little cheat sheet. So grep, awk, and sed, they support different flavors of regexes and different default behavior. So grep gives you basic, extended, and Perl compatible regular expressions, uses BREs as the default. Awk gives you basic and extended regular expressions, but it uses extended as the default. And then sed gives you basic and extended, again using basic as the default. Now, with awk, one little subtlety, the default is really basic regular expressions, but you'll likely be using a modern implementation like gawk, which uses ERE by default, and you're often going to be unaware of this since awk is usually a symbolic link to gawk. So if I execute this command on expanse, ls-l, and then the syntax here $, and in parentheses which awk captures the output, we could see that awk actually does point to gawk. All right, one last topic before we wrap up and talk very, very briefly about large language models. If you look in user bin, you'll normally see one awk, which is a symbolic link to gawk, one sed, and a whole bunch of different greps. So ignoring the symbolic links and the original grep, we're left with the following. So you can see there's a whole bunch of them: BZ grep, E grep, F grep, grep, message grep, P grep, ptar grep, and so on. I'm going to say there's only two of these that you actually need. Grep with -ere and -f options do everything that the deprecated egrep and fgrep do. Xzgrep searches for patterns in files compressed using compressed bzip2, gzip, lzma, and so on. And this covers all the functionality of bzgrep, zegrep, zfgrep, zgrep, and so on. And then the other ones are mostly used by Linux sysadmins. The reason I point this out is sometimes you're going to be working with large files and you large compressed files and you want to do searches on them. You don't need to uncompress them. You could use xzgrep directly, specify your regular expression, and then the name of the file. And xzgrep, based on the file extension, whether it's bz2, gz, xz, or capital Z, will interpret it correctly as a bzip, gzip, xz, or compressed file. All right, so finally, to wrap up, you may find that LLMs like ChatGPT are very useful for writing regular expressions, so why should I still study how to create them manually? And I'm going to give you, to me, two main motivations. First, the LLM might not do exactly what you want it to do. So I had gone to ChatGPT, and I give it the prompt: write a sed one-liner that replaces all instances of the string pair with 4x's, but only if it appears at the start or the end of the line. And then ChatGPT responded and said, here's a sed one-liner to replace pair with 4x's only if it appears at the start or the end of the line. But notice the subtle difference in the interpretation. I asked for the string pair, but ChatGPT assumed the word pair separated by spaces from other text. And I highlighted this here with those blue arrows. So the LLM might not do exactly what you want it to do. There may be subtleties in interpretation. Second, I find that sometimes it's just easier to write the regex yourself. So when I prompted ChatGPT to write a grep one-liner that outputs all lines in a file that contain the pattern A followed by exactly 2 or 3 occurrences of the string XYZ followed by B, it gave me a valid regex that did exactly what I wanted it to do. But I'm going to say, in this case, it was probably more effort to write that prompt than it was to write the grep statement. So many of you here come from, very, very mathematically intensive backgrounds, physics, engineering, bioinformatics, library sciences, and so on, where you're used to working with math and logic, and you may find that it's just easier to just write the regex than it is to express yourself in words. And then finally, and we won't go through all this slide, it's a lot of text, this is more for reference. This was ChatGPT's answer to the question in the previous slide, namely, since LLMs are so useful, why should I still know how to create them manually? And there's a lot of good information here. They mention understanding the basics, customization. These are really important. I've found over the years I've used, before LLMs, I would go to Stack Overflow a lot for programming suggestions. And even when I see the solution, I would have to struggle a little bit to figure out how to use that in my case. So if you understand the basics, you're going to be able to troubleshoot those regexes. You're going to be able to identify when they're not quite doing what you want, and you're going to be able to customize it better for your own solutions. And then finally, the last one I like to emphasize is critical thinking. Writing regexes manually force you to think critically about the problem you're solving. So with that, I'm going to wrap up. I'm going to say when combined with tools such as offset and grep, regexes give you a powerful way to search and manipulate text. Don't be overwhelmed by all the regex options. This was a lot of material to cover in 1 hour if you hadn't seen regexes before. Learn what you need to get started, then pick up the rest incrementally along the way. If you find that you just need alternation or you need the anchors, the caret and the dollar, start with that and bit by bit add the other features until you really understand LLMs. Be careful when you use when understand regexes. Be careful when you use LLMs to help you construct regexes. They're not 100% reliable, and it's often hard to specify in words exactly what you want the LLM to do. And then finally, regular expressions are not specific to offset and grep. Many programming languages, including R, Python, Perl, and C++, have regexes. Now, the syntax may be a little bit different, but everything that you learned here, all of the concepts, they're universal, and they will carry over to these other languages. And with that, I am going to stop the presentation. I am happy to take any questions.